Hello students, I Pooja Garg welcome you all in my online classes for class 10th, and today I am going to start chapter number 1 real numbers. Under this we'll do recapitulation and NCERT solutions related to exercise number 1.1 and 1.2. So before going to start this topic, do like and subscribe my channel Power of Mathematics, and don't forget to press bell icon for further notifications. So let us begin. Exercise number 1.1, based on Euclid's division lemma. According to this lemma, positive integers a and b, there exist unique pair of integers q and r such that a is equals to bq plus r, where r is greater than equals to 0, less than 5. Now exercise. In exercise 1.1, the very first question is, using Euclid's division algorithm, you have to find HCF of the following numbers. So the very first question is here 135 and 225. So here we have to apply Euclid division lemma. So what we'll do, as you know, 225 is greater than 135. So by applying Euclid division lemma, so what we get, A is equals to BQ plus R. And here we'll take A as 225 and B as 135, where R is greater than or equals to 0 and less than B. So as we have already discussed in the video how to apply this lemma, so for that we can do a rough work by showing a HCF of these two numbers by long division method. So the very first step is dividend is equals to divisor into quotient plus remainder. So when we divide 135 and this 225, ones are 135 remainder as 90. So the very first step, 225 is equals to 135 into 1 plus 90. Then I told in second step this divisor become dividend and the remainder become quotient. Remainder becomes divisor. So the next step is 90 ones are 90 and remainder is 45. So it means 90 into 1 plus 45. Now next step, this divisor becomes dividend, remainder becomes divisor, and 45 twos are 90 plus remainder as 0. So as we know, this last divisor is known as HCF. So hence the HCF of these two numbers is 45. So in this way we can apply Euclid's division lemma in any question for finding HCF. Now see the second part of this question, and here the question is 196 and we have to find another number is 38,220. So again we can see 38,220 is greater than 196. So by applying Euclid division lemma, A is equals to BQ plus R, where R is greater than equals to 0 but less than 5. So here this is the value of A and this is the value of B. Now when we divide, so in a single step only I am getting remainder as 0. So here we'll get only one step, that is dividend is equals to divisor into quotient plus remainder. So last divisor is HCF, that is 196. In the same manner we have one more part here, that is the number is 867 and 255. So in the same manner you can observe we got the HCF as 51. Now see the third question. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is a maximum number of columns in which they can march? So here you know this maximum represent means here we are going to find the HCF of these two numbers. Maximum means in case of maximum what we'll do, we'll find HCF. As this is a word problem related to HCF and LCM, so whenever we need to find the maximum, though we'll use HCF of those numbers. And again here we are using Euclid's division lemma. So in the same manner the maximum number of columns is equals to the HCF of these two numbers. So in the same manner we'll find the HCF of these two numbers. You can observe here. So the HCF is 8. It means the maximum number of columns is 8. If suppose I need to find here minimum, so in the case of minimum we'll find least common multiple, that is LCM. Now see another question, that is question number 2. So here we already discussed this type of question where we need to show. So here the second question, if you are observing, which is show that any positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5, where q is some integer. So here you know what we will do here, as they are asking about the any positive odd number, odd. So let a be any positive odd number and we will put b as 6. Now applying Euclid's division lemma, according to this, a is equals to bq plus r, where r is greater than equals to 0 but less than b. And if we'll put b as 6, so what we'll get? A is equals to 6q plus r. And here according to this, what will be the possible value of r? It can be 1, 0, 1, 2, 3, 4 or 5. Now when I'll take r as 1, we'll get a is equals to 6q. When r is 1, we'll get a as 6q plus 1. When r is 2, a as 6q plus 2, and so on. So till 5 we'll put the value of r. So at last we'll get 6q plus 5. Now in these case you can observe, in very first case we get a as even, second case a as odd, third case even, fourth case odd, even, and then odd. But according to this question, what we need to find? Positive odd number. So in how many cases I am getting positive odd number? So in this case when r is 1, in this case when r is 3, and in this case when r is 5. So it means any positive integer, odd integer, is of the form 6q plus 1, 6q plus 3 or 6q plus 5. Now see another question. Here you can observe, by Euclid's division lemma we have to show that the square of any positive integer. Now please remember this, square of any positive integer is of the form either 3m or 3m plus 1 when m is some integer. So in the same manner we'll continue this question. So here again we'll let a as a positive integer and we'll put b as 3. By Euclid's division lemma, a is equals to bq plus r, where r is greater than equals to 0 but less than 5. Now we are going to put b as 3. So what we'll get? A is equals to 3q plus r. In place of r, we'll replace it by now 0, 1 or 2 according to this condition. Now the very first step under this is when r is 0. When r is 0 means a is equals to 3q. A is equals to 3q means here actual I need to find the square. So it means a square is equals to 3q whole square, that is 9q square. So here I am taking 3 as common and rest factors inside the bracket. So in place of this 3q square I am going to put m, because m is any integer. So here what do I get? When r is 0 I converted it into which form? 3m. Same way r is 1, it means I'll get 3q plus 1. So again do squaring both sides. So here I'm going to apply identity a plus b whole square, that is a square plus b square plus 2ab. Now what I'm doing, I'm taking first and last term together and taking 3 as common. And rest of the factors remains in the bracket and this plus 1 separately. Now I'm going to replace this by m. That is what I get, 3m plus 1. And last is when r is 2, in the same manner I am going to apply identity. Till this step you can observe. Now what I am doing after this step, I am going to split this 4 as 3 plus 1. And I am going to take these 3 terms in one bracket and taking 3 as common. And rest factors inside the bracket. And here now again I am going to replace this whole bracket by m. So what do I get? 3m plus 1. So you are observing whether r is 0, 1 or 2. They are always of the form either 3m, 3m plus 1, 3m plus 1. So hence the square of any positive integer is of the form 3m or 3m plus 1. Now see the next question. Under this what we have to show? Euclid division lemma, but now the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Now you see the solution of this question. Again I am going to let a as a positive integer, where I am going to put b as 3. You know why 3? Because if I'll take it as 9, so it will be very long and lengthy, because 9 means less. I need to take the value of r as less than 9, all the values till 0. So here what I'll do, as you know 3 square is 9, so I'm going to put b as 3. Again by Euclid's lemma, I'll get this step. So here after putting the value, I'll get a is equals to 3q plus r, where r value can be 0, 1 or 2. Now when r is 0, I'll get a is equals to 3q, but now this time I need to find the cube, because here we need to find a positive integers whose cube is of the form either 9m plus 1 or 9m plus 8. So here I have done the cube of this. Now I am taking 9 as common and remaining factors inside the bracket. Now this factor I am going to replace by m, that is 9m. Second is when r is 1, means 3q plus 1, again cubing both sides, and here I am going to apply identity a cube plus b cube plus 3a square b plus 3ab square. So when I apply identity, I will get this. Now what I am going to do, I am going to take this first term, third and fourth term together and taking 9 as common, and this one is separately, and again I am going to replace this whole bracket by m. So it means 3m plus 1. And the third is when r is 2. In the same manner I am going to apply the identity. Now again I am going to take this term, third and fourth term together and take 9 as common plus 8 separately and replace this whole bracket by m. So you can observe in first case I replaced it by 9m, second 9m plus 1, third 9m plus 8. So here we can say that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Now exercise 1.2 based on fundamental theorem of arithmetic. According to this, every composite number can be expressed or factorized as a product of prime, and these factors is unique apart from the order in which the prime factors occurs. Next is LCM and HCF. Under LCM you know how to find product of the smallest power of each common prime factors, but in LCM we'll take the greatest powers. And the relationship between LCF and LCM is A into B is equals to LCM into HCF. Now let's begin. Now in the second exercise, see the first question, express each number as a product of its prime factor. So everybody know how to find the prime factors. So here the very first part is 140, and the prime factors of 140 as 2, 2, 5 and 7. So here we can rewrite it as 2 square into 5 raised to the power 1 into 7 raised to the power 1. So these are the prime factors of 140. And this basically method is known as prime factorization method. Next, 156. In the same manner, if you will find the prime factors of 156, you will be getting 2 square into 3 into 13. Third part, 3825. So if I am going to find the prime factors of this, and you can see here I am getting all the prime numbers and try to get in the ascending order. So factors are 3 square into 5 square into 17. Fourth part, 5009. So if we will find the prime factors of this, we'll get it as 5 into 7 into 11 into 13. Same way we have one more part in this. That is 7429. So if we will find prime factors, so you can see here it is very difficult to find the prime factors as the very first prime factor is 17. So 17, 19 and 23. It means 17 into 19 into 23 are the prime factors of this number. Now the second question is find LCM and HCF of the following pairs of integers, and we have to verify this. HCF into LCM is equals to product of two numbers. So again, for finding LCM and HCF, we are going to use prime factorization. As we have already discussed, HCF means what we'll do? Yes, we'll take the highest, we'll take the lowest power of the factor, prime factor. In LCM, we'll take the highest power. So let us find it out. First of all, prime factors. As 26 prime factors are 2 into 13 and 91 prime factors are 7 into 13. Now I'm making them same. Can I here write 7 raised to the power 0? So that it is convenient to find out the smallest or the greatest power. And here I can include 2 raised to the power 0. Now for HCF, we will see smallest power 2 power 1, 2 power 0. Which is smallest? 2 power 0 means 1. Among 7, which is smallest? 7 power 0, which is again 1. And here 13 power 1 is only the smallest. It means the HCF of these two numbers is 13. Now for LCM, we are going to take the greatest powers. Greatest power among 2 is power 1 means 2. Among 7, power 1 is 7 again. Among these two, greatest is power 1 means 13. So when we multiply all these three numbers, we'll get 182. Now verification, what we'll do in verification part? First we'll find LCM into HCF. See the verification here, LCM into HCF, which is equals to 182 into 13. We'll get it as 2366. And another side is product of two numbers. Which are the two numbers? That is 26 and 91. So product of these two numbers is again same, you can see. So hence verified. Now see the second part, that is 510 and 92. So again we can observe the prime factors of 510 is 2 into 3 into 5 into 17, and prime factors of 92 is 2 into 23. 2 square into 23. Now again I am making them same here. I included 23 power 0, 3 power 0, 5 power 0 and 17 power 0. So for HCF we'll see the smallest power. So among 2, which is smallest? Power 2 only. Among 3, which is smallest? 0 means 1. Among 5, which is smallest? 5 power 0, again 1. Among 17, which is smallest? Again 0, that is 1. And among 23, which is smallest? 0 power, means again 1. So it means HCF is 2, and for LCM you can find the greatest powers. So when we multiply all these numbers, we'll get it as 23,460. Now again see the verification part. LCM of these two numbers, this into this, we'll get it as 46,920. Same with the product of numbers, we'll get the same. It means hence verified. Suppose you are getting different answers, it means you did something wrong. Means either HCF is wrong or LCM is wrong. Means there is some mistake in the question. So in this way we can verify our answer whether HCF and LCM of that particular numbers are right or not. Now see the third part, 336 and 54. So in the same manner you can try it by your own. Now see the second question. Find LCM and HCF of the following integers by applying prime factorization. So method is almost same. So you can observe and you can try it. Here 12 factors, 2 square into 3. 15 factors, 3 into 5. 21 factors, 3 into 7. So you can observe here HCF and here LCM. How to find. Same way another numbers we have 17, 23, 29. So please observe, and third part you can try it by your own. That is 9, 8 and 25. Now see the fourth question is very easy. Given that HCF of 306 and 659 is 9 and we have to find LCM, and as we know this HCF into LCM is equals to what? Product of two numbers. Just put the values. HCF is 9. LCM we have to find it out. Product of two numbers means 306 and 657. So simply you solve it. Here this 9 will come in division. So when you simplified it, you will be getting as 22,338. So in this manner you can find LCM. Same way they can ask for finding HCF when LCM is given to you of two numbers. Now see the next question. Though this type of question we discussed in the video, check whether 6 raised to the power n can ends with 0 for any natural number n. So here what we'll do, 6 raised to the power ends with 0, it means it must be divisible by 10. And if it is divisible by 10 means the prime factors must be either 2 or 5 or the combination. But here you can observe 6 raised to the power n is equals to what? 2 into 3 means 6 whole power n. It means the only prime factors of 6 power n is what? 2 and 3. So here 5 cannot be the prime factor of this, because of uniqueness of fundamental theorem of arithmetic. So hence we can say that 6 power n cannot end with digit 0 for any natural number n. Next question, number 6. Explain why this number and this number are composite numbers. Here you can observe, first of all I am taking the very first example here, 7 into 11 into 13 plus 13. So can I write this 13 as 13 into 1, because 1 is a factor of each and every number. Now I am taking 13 as common by using distributive property. So here what is left? 7 into 11 plus 1. 77 plus 1, 78, and the prime factors of 78 are these. Now we can observe ultimately at last what we get, 2 into 3 into 13 power 2. So it can be expressed as a product of its prime. So here this is a composite number. Now you can try the second part by your own. So again you can write this 5 as 5 into 1, then take 5 as common. And the last question of this exercise here, again it's a word problem. Now you read the question first. There is a circular path around the sports field. Sonia takes 18 minutes to drive one round of the field, while the Ravi take 12 minutes for the same. And we have to suppose they start at same point at the same time in the same direction. So after how many minutes they will meet again, means we have to find the minimum time. Minimum means we are going to find their LCM. So if we want to find the minimum time, how much after how much they meet again at the starting points, in this case we need to find the LCM of this number. So LCM of this number, you know how to find. So first you see the prime factors of 18 and 12 are this and this. So LCM is what? Greatest powers here. So 2 square and 3 square, that is 36. It means Sonia and Ravi will meet again at a starting point after 36 minutes. Students, kindly see topic-wise PDF of all notes for chapter number 1, real numbers, attached in description box of each part. Thank you for listening and keep on practicing.